Look up at the night sky, and what do you see? A vast, glittering expanse of stars. Right, but here's the thing. Those stars aren't floating in empty space. The cosmos is far from empty. Between every star, every galaxy, there's something else, a hidden, invisible ocean of gas, dust, and energy so mysterious it makes up nearly 20% of our entire Milky Way. This is the interstellar medium, the silent, shadowy fabric of space itself, and what's lurking within it, secrets that defy our understanding of physics, ghostly signals with no clear source, and structures so strange they shouldn't even exist. Picture this: you're drifting through the void between stars, where temperatures swing from freezing cold to blistering heat in an instant. Here, particles thinner than a whisper collide, creating cosmic puzzles that have baffled scientists for decades. Somewhere in this darkness, there's radiation with no known origin. Somewhere, there's dust that shouldn't survive the harshness of space, yet it does. And somewhere, there are forces at work we haven't even begun to comprehend. This isn't just empty space, it's a dynamic, chaotic frontier, and we've barely scratched its surface. Today, we're diving deep into 30 of the most mind-bending mysteries hidden within the interstellar medium. From eerie radio waves that seem to echo from nowhere, to colossal magnetic fields twisting in ways that shouldn't be possible, each one of these enigmas challenges what we think we know about the universe. And the wildest part, solving even one of them could rewrite the textbooks. So if you've ever wondered what's really out there between the stars, buckle up. Because we're about to explore the unseen, the unexplained, and the downright unbelievable. Ready to uncover the secrets of the cosmos, let's begin. Think of the universe not as a scattering of disconnected galaxies, but as a vast, intricate spiderweb, one woven from threads of glowing gas so massive they could wrap around the Milky Way 1,000 times over. These are the cosmic filaments, the hidden highways of the cosmos. Stretching millions of light years, they form a labyrinth of ionized hydrogen, a ghostly network that binds galaxies together like beads on a string. And here's what blows scientists' minds. Nearly half of all the normal matter in the universe, the stuff stars, planets, and you are made of, is hiding inside these wispy tendrils, drifting in a state so diffuse we barely detect it. What keeps them from collapsing or dispersing? Magnetic fields, for one, invisible forces that may braid these filaments into stable structures. But the real shocker. Recent supercomputer simulations suggest these threads don't just sit there. They act like cosmic wind tunnels, funneling superheated gas between galaxies at speeds that defy logic. Picture a hurricane, but one that rages across millions of light years, sculpting galaxies as it goes. Some researchers even think these filaments could be the secret ingredient behind why galaxies grow where they do, like invisible rivers nourishing celestial ecosystems. Yet for all their importance, these filaments are maddeningly elusive. Their gas is so thin, a single cubic meter might contain just a few atoms, far emptier than the best vacuum we've ever created on Earth. That's why spotting them often relies on their faint glow when illuminated by the light of distant quasars, like catching cobwebs in a flashlight beam. And just when we think we understand them, new observations throw curveballs. Some filaments appear to be far hotter than predicted, as if some unseen energy is pumping through them. Others bend in ways that suggest forces we haven't even named yet are at work. So next time you gaze at the night sky, remember, the real drama isn't just in the stars. It's in the spaces between them, where these colossal threads weave the universe itself into shape. Deep in the interstellar void, far from the glow of any star, lie some of the universe's best-kept secrets, dark molecular clouds. These colossal, shadowy structures are the nurseries of the cosmos, places so dense and cold that they swallow starlight whole, rendering themselves invisible to ordinary telescopes. Yet inside these cosmic vaults, the raw ingredients of new stars and planets swirl in a chaotic dance. their chemistry so bizarre it includes floating clouds of alcohol and even sugar molecules. What makes these clouds truly baffling isn't just their frigid temperatures, often just a few degrees above absolute zero, but the sheer complexity of the molecules they contain. Scientists have detected everything from formaldehyde to vinyl alcohol drifting in these voids, organic compounds that shouldn't survive the harshness of space. But the biggest puzzle of all, a ghostly signal picked up by radio telescopes over 3 decades ago, emitted by an unknown molecule scientists still can't identify. Dubbed the mystery molecule, its spectral fingerprint defies all known chemistry, lurking in these clouds like a cosmic cipher waiting to be cracked. How does such intricate chemistry thrive in an environment that seems hostile to life's building blocks? One theory suggests that the icy surfaces of dust grains inside these clouds act as cosmic laboratories where atoms stick together in unique ways, shielded from destructive radiation. Another mind-bending possibility, these molecules might form not in the clouds themselves, but in the violent aftermath of dying stars ejected into space and preserved in these frozen vaults. Yet the deeper we look, the stranger it gets. Some of these clouds harbor structures so massive they could warp space-time itself, their gravitational pull bending light into eerie arcs. Others appear to be threaded with magnetic fields strong enough to shape entire star systems, guiding gas into swirling spirals that collapse into newborn suns. And lurking within them all is that same enigmatic signal, whispering its unsolved riddle across the light years. So while these dark clouds may seem like empty voids, they're anything but. They're the universe's hidden workshops where the impossible becomes routine, and where every discovery forces us to rewrite the rules of chemistry, physics, and our own cosmic origins. The next time you stare at a seemingly black patch of sky, remember, it might just be one of these enigmatic clouds hiding secrets we've only begun to imagine. Orion's sword hangs in the night sky, a glittering emblem of cosmic beauty, but just beyond its familiar stars lies something far stranger. Surrounding the entire constellation is an invisible wall, a 500 light-year wide bubble where the interstellar medium simply stops. It's as if some unseen force drew a boundary in the void, pressing pause on the drifting gas and dust that fills the rest of our galaxy. Astronomers call it the Orion supershell, and it's one of the most puzzling structures in our cosmic neighborhood. What could carve out such a perfect, colossal void? One leading theory points to the ghosts of long-dead stars. Imagine a series of supernova explosions so powerful they could outshine entire galaxies, detonating in sequence over millions of years. Their combined stellar winds might have blown away the surrounding gas like a cosmic hurricane clearing fog. The Orion Nebula's massive young stars, known as the Trapezium Cluster, could be heirs to this ancient violence, their own fierce winds now sustaining the bubble. But there's a catch. Recent data from the Gaia spacecraft reveals gaps in this story. The bubble's edges are too sharp, too well defined, as if something else is actively maintaining them. That's where the wilder theories come in. Some researchers suggest monstrous magnetic fields, invisible lines of force woven through space, could be acting like a celestial fence, corralling the interstellar medium into this precise boundary. Others speculate about turbulence in the fabric of spacetime itself, or even the gravitational echoes of dark matter we can't yet detect. The Gaia mission's precise star mapping added another twist. The bubble is expanding unevenly, with some regions accelerating faster than physics predicts. It's almost as if the bubble is alive, reshaping itself in defiance of known laws. What's clear is that this isn't just an empty space, it's a laboratory for forces we barely understand. The Orion supershell challenges our assumptions about how the interstellar medium behaves, and every new observation deepens the mystery. So the next time you spot Orion's belt, remember, you're not just looking at stars. You're peering into a cosmic construction zone where the rules are still being written. starlight doesn't always travel untouched across the cosmos. As it passes through the interstellar medium, something strange happens. Hundreds of dark, narrow lines appear in its spectrum, as if invisible hands have drawn shadows across its rainbow. These are diffuse interstellar bands, or DIB, and they've been one of astronomy's most stubborn riddles for over a century. No one knows exactly what's causing them. They're like cosmic graffiti, tagging starlight with signatures we can't yet decode. The leading suspects: carbon-based molecules, possibly vast chains of carbon atoms drifting through space, or sprawling, ringed structures called polycyclic aromatic hydrocarbons, PAHs for short. Think of them as soot from cosmic fires, remnants of dying stars or shattered comets. But here's the catch: lab experiments can't perfectly recreate these absorption lines. Even when scientists mimic space conditions, some DIBs stubbornly refuse to match any known substance. It's as if the universe is hiding a whole new class of chemistry in plain sight. Why does this matter? Because these bands aren't just a curiosity, they could be galactic fingerprints. Each line, each shadow in starlight, might reveal the exact makeup of the interstellar fog between us and distant stars. Imagine being able to read the chemical history of the Milky Way just by studying these spectral scars. Some researchers even suspect DIBs could hint at organic molecules crucial for life, scattered across the void long before planets formed. Yet the deeper we look, the weirder it gets. Some DIBs change intensity depending on which direction you're looking, suggesting these mystery molecules aren't evenly spread but clumped in strange, invisible reefs. Others appear stronger in regions with intense radiation, defying expectations that harsh starlight should break them apart. And then there are the outliers, bands so rare they've only been spotted a handful of times, like cosmic ghosts passing through our telescopes. What's clear is this: the interstellar medium isn't just empty space. It's a vast dynamic chemistry lab brewing compounds we've yet to name. And until we crack the code of these spectral shadows, a fundamental piece of the universe's story remains just out of reach. So the next time you hear about astronomers studying starlight, remember they're not just looking at the stars, they're detectives deciphering the secrets written in the darkness between them. In the heart of the Milky Way, near the constellation Sagittarius, an eerie arc of radio waves stretches across the sky, 120 degrees wide, like a silent alarm ringing from the depths of space. This is the radio loop I, a structure so vast it could swallow our solar system 1,000 times over. For decades, astronomers believed it was the ghostly echo of a supernova that exploded 3 million years ago, a stellar death so powerful its shockwaves still ripple through the interstellar medium. But new observations are turning that story upside down, revealing something far stranger lurking in the data. The Planck satellite, mapping the cosmos in microwave light, painted Loop I as a textbook supernova remnant, a bubble of hot gas expanding into space. But when the Meerkat radio telescope in South Africa trained its ultra-sensitive antennas on the same region, it saw something wildly different. Filaments and ridges twisted into shapes that defy the smooth, symmetrical blast we'd expect from an ancient explosion. Instead, the structure resembles a tunnel, a cosmic wormhole carved through the interstellar medium by forces we don't yet understand. What could create such a contradiction? One tantalizing possibility involves the local bubble, a cavern of low-density gas surrounding our solar system, thought to be sculpted by multiple supernovae over millions of years. Loop I might not be a single remnant at all, but part of a sprawling network of cavities like rooms in a galactic labyrinth, connected by tunnels of magnetized plasma. If true, it would mean the interstellar medium isn't just a chaotic void, but a carefully sculpted landscape, shaped by overlapping stellar winds and explosions like a cosmic game of billiards. But the real mystery lies in the details. Some sections of Loop I glow with synchrotron radiation, a telltale sign of electrons spiraling at nearly light speed around magnetic field lines. Yet other areas show bizarrely low polarization, as if the magnetic fields there are tangled beyond recognition. Could this be evidence of unseen turbulence or even dark matter's gravitational influence warping the structure from within? Every new observation deepens the enigma. The Mercalli data reveals intricate braids of radio emission threading through Loop I, structures so delicate they shouldn't survive the violence of interstellar space. Meanwhile, Planck's wider view suggests the entire loop might be part of a larger, interconnected web of bubbles, hinting that what we're seeing isn't an anomaly, but a hidden rule of how galaxies evolve. So is Loop I a supernova's gravestone or a portal into the invisible architecture of the Milky Way? Right now, the answer is both and neither. It's a reminder that even the seemingly quiet spaces between stars are alive with forces we're only beginning to decode. And as telescopes grow sharper, this radio whisper from the depths of Sagittarius may yet reveal secrets that rewrite our map of the cosmos. Rising from the galactic center like twin titans, two colossal bubbles of gamma-ray light stretch 25,000 light-years into space, one above the Milky Way, one below. Discovered by the Fermi telescope over a decade ago, these structures glow with the fury of a billion suns, yet their origin remains one of the universe's most heated debates. Dubbed the Fermi bubbles, they're not just glowing relics of the past, they're leaking, changing, and revealing secrets that could rewrite our understanding of the galaxy's violent heart. At first glance, the bubbles seem like scars from an ancient catastrophe. Some theorists argue they're the aftermath of a quasar eruption, a time when the Milky Way's supermassive black hole, Sagittarius a star, feasted on stars and gas, belching out energy so fierce it punched holes in the interstellar medium. Others propose something even wilder, dark matter particles colliding and annihilating in a sustained, invisible fireworks show near the galactic core. But the most baffling clue surfaced in 2023 when astronomers noticed high-energy particles streaming from the bubble's edges like steam from a pressure cooker. These aren't just static structures, they're dynamic, evolving entities, actively interacting with their surroundings in ways no model predicted. What's fueling this cosmic leak? One camp points to galactic winds, rivers of charged particles whipped up by the black hole's past activity, still surging outward like a slow-motion tsunami. Another theory suggests magnetic reconnection, a process where tangled field lines snap and fling particles into space at near light speeds. But the strangest twist comes from neutrino detectors, which have spotted faint signals aligning with the bubble's edges. If confirmed, this could mean they're not just emitting light, they're shooting out ghostly particles that pass through entire planets unnoticed. The implications are staggering. If the bubbles stem from dark matter, their structure could reveal the invisible scaffolding of the cosmos. If they're quasar relics, they'd prove our galaxy was once a quenched monster, temporarily as bright as the most luminous objects in the universe. And if their leaking particles are a new phenomenon, that might hint at processes we've never even imagined, a hidden engine buried in the Milky Way's core, still churning out cosmic mysteries. Every new observation peels back another layer. The bubble's gamma rays don't match any known astrophysical source perfectly, and their sharp edges suggest they're contained by some unseen force, like soap films stretched across the void. Even their shape defies simple explanations. Some regions bulge outward, while others taper into tendrils that seem to dissolve into the interstellar medium. It's as if we're watching a cosmic inkblot test, where each interpretation reveals more about our own theories than the universe's true nature. So while the Fermi bubbles might look like silent monuments, they're anything but. They're a roar from the galaxy's depths, a reminder that even our home in the cosmos hides violent, beautiful enigmas. And as telescopes grow sharper, these twin beacons may finally crack open the secrets they've guarded for millions or even billions of years. Somewhere in the vast darkness between galaxies, invisible bullets are screaming through the cosmos, particles so tiny they pass through entire planets without slowing down. yet packing energies 1,000,000 times greater than anything our most powerful colliders can produce. These are cosmic rays, specifically ultra-high-energy neutrinos, and their origins are one of the interstellar medium's most perplexing puzzles. Imagine a detective story where the clues lead not to a suspect but to an empty room, because when scientists trace these ghostly particles back to their source, they often find nothing. Just voids of empty space where no known cosmic powerhouse should exist. The mystery begins deep beneath the ice of Antarctica, where the IceCube observatory lies buried like a giant telescope turned upside down. Instead of gazing at the stars, it stares downward, waiting for the rare flash of blue light that signals a neutrino's fleeting interaction with the ice. Each one is a cosmic breadcrumb pointing back to where it came from. But here's what stumps researchers. Many of the highest energy neutrinos seem to originate in regions devoid of supernova, black holes, or any other obvious particle accelerators. It's as if the universe has invisible railguns hidden in the void, flinging these particles across billions of light years without leaving a trace. One radical theory suggests the answer lies in the interstellar medium itself, not as empty space, but as a turbulent highway of magnetic fields and shockwaves. Picture a cosmic pinball machine where particles get ricocheted between collapsing gas clouds or tangled magnetic filaments, gaining energy with each rebound until they're ejected at unimaginable speeds. Some simulations even propose that dark matter tsunamis, waves of invisible matter sloshing through galaxies, could be carving out hidden accelerators in these seemingly barren regions. But the plot thickens. In 2022, IceCube detected a neutrino linked to a distant blazar, a supermassive black hole spearing the cosmos with jets of plasma. Finally, a smoking gun, except when astronomers looked closer, the numbers didn't add up. Blazars can't account for all high-energy neutrinos, leaving most without a plausible source. This discrepancy has birthed the intergalactic accelerator hypothesis. Colossal structures like galaxies spanning shockwaves or decaying dark matter particles might be lurking in the voids, acting as stealthy particle colliders on a scale we've never imagined. What's truly eerie is how these neutrinos defy expectations. They arrive from all directions with no pattern, no preferred source, just an endless, enigmatic rain from the darkest corners of space. Some might be ancient, traveling since the universe's youth. Others could be newborn, hurled our way by events so extreme they warp the fabric of spacetime itself. And with each detection, we're left with more questions than answers. Why do some voids seem to emit neutrinos while others stay silent? What unseen physics could possibly explain their outrageous energies? For now, these ghost particles remain cosmic envoys, whispering secrets from realms we can't yet see. Every one that streaks through the ice is a challenge, a dare to rethink our understanding of how the universe works. And as detectors grow more sensitive, we might finally catch these phantoms in the act, revealing the invisible engines that have been hiding in plain sight all along. Our solar system isn't just drifting through empty space, it's sailing through a strange, wispy cloud of superheated gas known as the Local Fluff. This 30-light-year-wide bubble of interstellar material surrounds us like a ghostly embrace, with temperatures soaring to over 6,000 degrees Celsius, hotter than the surface of the sun. But here's the catch: this cloud should have evaporated eons ago. The sheer energy of nearby stars and supernova explosions should have blown it apart like smoke in a hurricane. Yet somehow, against all odds, it's still here. And when NASA Voyager probes pierced its boundary in 2012, they uncovered something even more baffling: a magnetic field 3 to 4 times stronger than anyone predicted, warping space around us in ways we still don't fully understand. What's holding this fragile cloud together? One theory points to the local bubble, the massive cavity carved out by ancient stellar explosions, whose walls might be acting like a cosmic pressure cooker, trapping the fluff inside. Another idea suggests that the cloud's own magnetic fields are intertwined like an invisible net, preventing it from dissipating. But the real shock came from Voyager's measurements. Those unexpectedly intense magnetic lines aren't just stronger, they're also weirdly organized, almost as if some unseen force is sculpting them into precise patterns. The implications are staggering. If magnetic fields this powerful can exist in such a tenuous environment, it means our understanding of interstellar physics might be missing a crucial piece. Normally, gas this hot and thin should be chaotic, its particles too spread out to sustain a stable magnetic structure. Yet the fluff defies that logic, its field lines threading through space with eerie resilience. Some researchers speculate this could be evidence of a larger, hidden magnetic framework woven throughout the galaxy, a cosmic web we've only just begun to detect. But the biggest question remains, how does this affect us? The Local Fluff's magnetic field might be the reason our solar system hasn't been bombarded by more harmful cosmic rays. Like an invisible shield, it could be redirecting high-energy particles away from Earth, subtly shaping the space weather around us, yet it also raises new mysteries. Why hasn't this cloud mixed with surrounding material? What's replenishing its energy to keep it from fading into the void? Every new discovery peels back another layer. Recent data from interstellar probes suggests the fluff's boundary isn't smooth but rippled, as if buffeted by unseen currents. Somewhere out there, in the darkness just beyond our solar system, forces we can't yet name are at work rewriting the rules of how gas, magnetism, and empty space interact. And until we crack this puzzle, we're left with a humbling truth. Even our own cosmic backyard holds secrets we're only beginning to uncover. Gazing toward the constellation Gemini, astronomers have stumbled upon a cosmic paradox, a pulsar named Geminga, spinning wildly as it hurtles through space, leaving behind an 800-light-year-long trail of gamma rays glowing like a ghostly wake. This celestial speedster, born from a supernova explosion 300,000 years ago, should be surrounded by a swirling storm of debris, shattered stellar remnants, and particles blasted outward by its violent birth. Yet when telescopes scan the area, they find nothing. No shattered nebula, no scattered gas, just an eerie void where the wreckage ought to be. It's as if something has swept the cosmic floor clean, erasing all traces of Geminga's past. The leading suspect, dark matter, the universe's most elusive substance. Some theorists propose that Geminga's passage might be triggering dark matter particles to annihilate one another, converting their mass into pure energy that dissipates without a trace. Imagine an invisible sponge mopping up the pulsar's debris, leaving only gamma rays as a faint receipt of the transaction. Others suggest an even wilder possibility. Geminga's powerful magnetic field, stretching light years into space, could act like a colossal vacuum cleaner, funneling particles away at near light speeds before they have a chance to clump together. But the plot thickens. Recent observations reveal that Geminga's gamma-ray tail isn't just smooth, it's braided with strands of energy twisting like a cosmic rope. This bizarre structure hints at forces beyond standard physics, possibly interactions with undiscovered particles or turbulence in the interstellar medium itself. Even more perplexing, the tail flickers unpredictably, as if something invisible is tampering with its flow. Could unseen dark matter clumps be brushing past, distorting the signal? Or is the pulsar's rapid spin generating shockwaves that scramble particles into oblivion? The implications reach far beyond Geminga. If dark matter is indeed responsible, studying this pulsar could give us a blueprint for detecting it elsewhere, turning gamma-ray tails into cosmic dark matter detectors. And if magnetic fields are the culprit, it would mean the interstellar medium is far more dynamic than we thought, with hidden forces sculpting gas and dust on scales we've barely begun to map. Either way, Geminga's missing matter isn't just a curiosity, it's a clue, one that could rewrite our understanding of how the universe hides its secrets. So while this pulsar races silently through the void, it's not just leaving a trail of light. It's dragging a mystery behind it, one that challenges everything we think we know about the space between the stars. Our solar system sits in an unsettling cosmic anomaly, a vast, almost empty bubble stretching over 2 billion light-years, where galaxies are scarce and the usual hum of matter falls eerily silent. Astronomers call it the KBC void, named after the scientists who first mapped it, and it challenges everything we thought we knew about the universe's structure. If the cosmos were a bustling city, this region would be a ghost town with 20% fewer stars, galaxies, and dark matter than the surrounding universe. But here's the twist: some researchers argue it might not even exist. The debate over whether the KBC void is real or just a trick of incomplete data has ignited one of the fiercest controversies in modern cosmology. The void's existence hinges on a paradox. On one hand, meticulous galaxy surveys show a striking dip in density around the Milky Way, as if we're floating in a cosmic oasis surrounded by desert. On the other, critics point out that our telescopes might be missing faint galaxies hidden behind dust or drowned out by the glow of nearby stars. The controversy deepened in 2023 when new simulations suggested the void could explain another cosmic headache, the Hubble tension. This is the stubborn discrepancy between how fast the universe seems to be expanding based on nearby measurements versus observations of the ancient cosmos. If the KBC void is real, its gravitational weirdness could be subtly distorting our local measurements, throwing off calculations like a hidden weight on a scale. But the wildest possibility, the void might not be an accident at all. Some theorists speculate it could be the imprint of an ancient collision with another universe, a bruise left in the fabric of space-time from a multiversal encounter we can't yet prove. Others suggest dark energy, the mysterious force accelerating the universe's expansion, might behave differently here, repelling matter into sparser regions. And then there's the unsettling alternative. What if we're wrong about gravity itself? Modified theories like Lyman propose that gravity works differently on cosmic scales, potentially creating illusions of voids where none exist. The stakes couldn't be higher. If the KBC void is real, it upends the cosmological principle, the long-held assumption that, on large scales, the universe is uniform everywhere. Confirming it would mean we live in a special, perhaps even freakish pocket of space, a realization as humbling as Copernicus discovering Earth wasn't the center of the solar system. But if it's an illusion, the Hubble tension remains unresolved, leaving cosmologists scrambling for answers. Right now, the truth lies somewhere in the data. Upcoming telescopes like the Vera Rubin Observatory promise sharper surveys, hunting for the faint galaxies that could settle the debate. Until then, the KBC void lingers as one of the universe's most tantalizing maybes, a shadow on the cosmic map, challenging us to question not just where we are, but how well we truly understand the grand structure of reality. Deep in the cosmic void, floating like islands of ultraviolet fire, lie some of the universe's most enigmatic structures, lyman-alpha blobs. These colossal clouds of hydrogen gas, some spanning hundreds of thousands of light-years, glow fiercely with the same wavelength of light that hydrogen emits when it's energized. But here's what makes them utterly baffling. Many of these blobs drift in the blackness of intergalactic space, far from any stars or galaxies that could be heating them. It's like finding a neon sign blazing in the middle of an empty desert with no power source in sight. Take the SSA-22 protocluster, a gathering of young galaxies 13 billion light-years away. At its heart floats one of the largest lyman-alpha blobs ever discovered, a swirling, city-sized mass of hydrogen shining brighter than entire galaxies. The puzzle: there's no obvious source of energy to explain its brilliance. No nearby quasars, no burst of star formation, just this luminous enigma hanging in the dark. So how does it stay lit? One leading theory involves something called cold flow accretion, rivers of pristine hydrogen gas, untouched by stars, streaming in from the cosmic web. These flows might slam into each other at high speeds, shock heating the gas just enough to make it glow without ever forming stars. Picture two fire hoses blasting water into an empty pool. The collision creates turbulence and spray, even if there's no fire to put out. In this scenario, the blob is a cosmic traffic jam where gas from the early universe piles up, trapped by gravity's pull. But there's a rival explanation that's even more intriguing: hidden black holes. Some astronomers argue these blobs could be the fingerprints of supermassive black holes in their infancy, gorging on gas so furiously they flood their surroundings with radiation, without yet forming the bright accretion disks we usually associate with quasars. It's like hearing an engine roar but seeing no car. The energy signature is there, but the source remains cloaked in darkness. The debate gets even thornier when you zoom in. The SSA-22 blob's light isn't smooth, it's clumpy with bright knots and shadowy gaps. Cold flow models struggle to explain this patchiness, while black hole theories can't quite account for the blob's sheer size. That's led to wilder ideas like dark matter annihilation or even exotic physics processes we haven't yet imagined pumping energy into the gas. What's at stake isn't just solving a cosmic lightbulb mystery. These blobs might be the nurseries where today's giant galaxies were born, their glow a fossilized snapshot of the universe's most violent growing pains. And with new telescopes like the James Webb Space Telescope peering deeper than ever, we're on the verge of catching these structures in the act, revealing whether they're cosmic construction sites, black hole cradles, or something even stranger. So the next time you hear about glowing gas in space, remember, not all light comes from stars. Some of it flickers from the void itself, a relic of forces so vast and ancient we're only beginning to grasp their echoes. In the depths of intergalactic space, a mystery crackles across the cosmos: fast radio bursts, or FRB. Those fleeting blasts of radio waves so powerful they outshine entire galaxies for mere milliseconds. But among these cosmic fireworks, one source stands apart: FRB 121102, the first known repeater, sending its signals not just once, but in erratic, unpredictable patterns that have baffled astronomers for years. What makes this object even stranger? Some of its pulses arrive not as single bursts, but as split-second doublets, paired flashes separated by less than a millisecond, as if the universe itself is stuttering. So what could possibly create such bizarre behavior? One leading theory points to magnetars, super-dense, hypermagnetic neutron stars that occasionally unleash starquakes, cracking their ultra-rigid crusts and releasing unimaginable energy. Picture a frozen lake suddenly fracturing under pressure, sending shockwaves rippling outward. If FRB 121102 is a magnetar, these doublets could be echoes of seismic waves bouncing through its interior, each tremor slightly offset as it reaches the surface. But there's a wilder possibility: plasma lensing. The interstellar medium isn't empty, it's filled with turbulent clouds of charged particles. If a burst passes through one of these clouds, it could bend and split the signal, like light refracting through a jagged prism. Recent data from the CHIME telescope reveals FRB 121102's doublets sometimes arrive at slightly different frequencies, hinting at this very phenomenon. It's as if the bursts are navigating a cosmic obstacle course, their paths twisted by invisible magnetic whirlpools. Then, of course, there's the elephant in the room. Could these repeating patterns be artificial? The idea of alien beacons isn't entirely dismissed. Some scientists argue that the doublet's precision warrants at least considering non-natural origins. But Occam's razor favors astrophysics over extraterrestrials, especially since 2023 observations linked similar bursts from other sources to extreme stellar mergers. The real breakthrough came when researchers noticed something peculiar in FRB 121102's doublets. Their spacing isn't random. Some follow a near-mathematical rhythm, suggesting an underlying mechanism far more structured than chaos. Could this be evidence of a neutron star's magnetic field lines snapping and reconnecting, like cosmic rubber bands stretched to their limit? Or perhaps the bursts are modulated by an orbiting companion, a hidden partner tugging at the source like a puppeteer. Every new pulse from this distant enigma peels back another layer. The chime data reveals bursts so brief they challenge our detector's limits, yet packed with clues about the universe's most extreme environments. Whether starquakes, plasma trickery, or something even stranger, FRB 121102 isn't just a mystery, it's a masterclass in how much we still have to learn about the forces shaping the cosmos. And with each split-second doublet, it whispers a challenge: decode me if you can. Rising like twin echoes of the Fermi bubbles, another pair of colossal structures stretches across the Milky Way. The E-Rosetta X-ray bubbles, discovered in 2020 by the German-Russian space telescope of the same name. These towering formations glow faintly in high-energy X-rays, each one a staggering 45,000 light-years tall, dwarfing even our entire solar system. But while they share similarities with their gamma-ray cousins, these bubbles tell a radically different story, one that points to a violent tantrum from our galaxy's central black hole just 15 million years ago, a blink in cosmic time. What makes these X-ray bubbles so special? Their symmetry. Unlike the Fermi bubbles, which show jagged edges and uneven emissions, the E-Rosetta structures are near-perfect mirror images, ballooning outward from the galactic center with eerie precision. This level of balance suggests a single catastrophic event, a sudden eruption from Sagittarius, a star, our supermassive black hole, rather than the slow buildup of multiple explosions. Imagine a dormant volcano waking with a single, earth-shaking blast, its ash clouds rising in perfect twin plumes. That's the scale of violence we're talking about here. The smoking gun lies in the bubble's composition. They're filled with ultra-hot plasma, supercharged gas heated to millions of degrees, but also laced with heavier elements like iron and neon, telltale signs of material ripped from stars or devoured by the black hole itself. This chemical fingerprint matches what astronomers would expect from a brief but furious feeding frenzy, where Sagittarius, a star, gulped down a massive clump of gas, or even a star, then belched out the leftovers in two opposing jets. Yet the mystery deepens when you look closer. The E-Rosetta bubbles aren't just expanding, they're still faintly glowing, as if energy is being continuously pumped into them. Some researchers think this could mean the original eruption isn't entirely over. Shockwaves might still be reverberating through the interstellar medium, reheating the gas like a cosmic microwave. Others argue it's evidence of an ongoing tug-of-war between the black hole's outburst and the galaxy's magnetic fields, which could be funneling particles back into the bubble's edges. The most tantalizing clue: these X-ray structures align almost perfectly with the Fermi bubble's axes, as if both were sculpted by the same unseen hand. That's led to a spine-chilling possibility. What if Sagittarius, a star, has periodic violent episodes, erupting every few million years in cycles we're only beginning to map? If true, our galaxy's heart isn't just dormant, it's on a timer, building toward its next catastrophic release of energy. So while the E-Rosetta bubbles might look like ghostly relics, they're actually a snapshot of something far more dynamic, a black hole's temper tantrum frozen in X-ray light. And as telescopes grow sharper, these structures may reveal not just the Milky Way's past, but its volatile future. Floating in the depths of space like a cosmic bullseye, Hoag's object defies every expectation of what a galaxy should look like. At its core lies a dense, yellow-hued cluster of ancient stars, surrounded by a perfect sapphire blue ring of younger, hotter stars separated by a gaping void 120,000 light-years wide. So empty it's as though some celestial hand carved out the interstellar medium with surgical precision. This isn't just a galaxy, it's a riddle wrapped in starlight, challenging our assumptions about how galaxies form and evolve. Theories about its origin swing between two extremes. One camp argues it's the ghost of a colossal collision, a smaller galaxy plunging through the heart of Hoag's object billions of years ago, its gravity rippling outward like a stone dropped in water, leaving behind a ring of newborn stars in its wake. But there's a problem: no visible debris, no trail of scattered stars, no sign of the perpetrator. It's a cosmic crime scene with no suspect. That's led to a wilder idea, the quasar splash scenario. Imagine the galaxy's core, once a ferocious quasar, erupting with so much energy it blasted away surrounding gas and dust in two opposing jets, leaving behind a near-perfect vacuum. Over time, the remaining material at the edges collapsed into that stunning blue ring, like foam clinging to the rim of a drained bathtub. Then came 2022's curveball. Australia's IceCube radio telescope began spotting similar structures, strange, ring-shaped anomalies dubbed odd radio circles or ORCs scattered across the sky. These faint, gargantuan rings, visible only in radio wavelengths, share eerie similarities with Hoag's object, vast, symmetrical, and seemingly devoid of obvious triggers. But here's where it gets fascinating: some ORCs encircle entire galaxies, while others float in isolation, unmoored from any visible stellar anchor. Are these the aftermath of ancient quasar eruptions, galactic mergers, or something entirely unknown? The plot thickens when you examine Hoag's object's finer details. Recent spectroscopy reveals its inner and outer stars rotate at nearly the same speed, a harmony that shouldn't exist if the ring formed from a violent encounter. Meanwhile, the ORCs show polarized radio emissions, hinting at shockwaves rippling through the interstellar medium, perhaps relics of past cataclysms. Could these structures be signposts of a universal phenomenon we've overlooked, a hidden phase of galactic evolution where black hole outbursts or dark matter interactions sculpt space itself? What's clear is this: Hoag's object and its newfound cousins refuse to fit neatly into our cosmic narratives. They're outliers, exceptions that might just rewrite the rules. And as telescopes peel back more layers of these enigmatic rings, one thing becomes certain: the universe has a flair for the dramatic, painting mysteries across the void that demand we rethink everything we thought we knew. There's a cosmic tsunami racing toward the Milky Way, and its name is Smith's Cloud. Stretching 11,000 light-years long, this colossal river of hydrogen gas is hurtling through space at nearly 2 million miles per hour on a direct collision course with our galaxy's outer disk. But here's what makes this celestial juggernaut truly bizarre. It's wrapped in a magnetic sheath, an invisible force field of unknown origin that's defying every expectation of how gas behaves in the void between galaxies. Hubble's sharp-eyed observations reveal this sheath acting like a cosmic straitjacket, binding the cloud's hydrogen into an unusually dense, coherent structure instead of letting it dissipate into the interstellar medium. Normally, a gas cloud this massive should have frayed apart eons ago, shredded by galactic tides or torn asunder by collisions with other intergalactic material. Yet Smith's Cloud remains eerily intact, its magnetic shield resisting the chaos of deep space like an armored ship plowing through a storm. The question isn't just where this shield came from, it's what happens when this titanic projectile slams into the Milky Way. Some simulations suggest the impact could ignite a fireworks show of star formation, as the compressed gas collapses under its own gravity, birthing millions of new suns along the galactic outskirts. Others warn the cloud might simply shatter on contact, its atoms scattering like confetti into the halo, but the wildest theory, that magnetic sheath might be the key. If it survives entry, it could funnel the cloud's gas into focused streams, creating concentrated starburst zones instead of a diffuse spray. Imagine a meteor striking Earth's atmosphere, but instead of burning up, it's steered by an unseen force to land in a precise location. The origin of that magnetic shield deepens the mystery. Some astronomers argue it's a relic of the cloud's violent past. Perhaps it was ripped from the Milky Way's disk eons ago, dragging magnetic fields with it like cosmic scars. Others propose something more exotic, dark matter interactions or even the imprint of a long-dead galaxy, its magnetic ghost still clinging to the gas. The most tantalizing clue, the sheath's alignment doesn't match the Milky Way's native magnetic fields, hinting at an external source. As Smith's cloud nears its fateful rendezvous, due in roughly 30 million years, it's more than just a celestial curiosity. It's a live experiment in galactic physics, a chance to witness how material from the intergalactic wilderness integrates with a galaxy like ours. And with every new observation, this enigmatic structure whispers a tantalizing secret: the space between galaxies isn't empty. It's threaded with invisible forces, sculpting matter in ways we're only beginning to comprehend. Imagine a hole in the universe so vast you could drop the entire Milky Way into it and still have room for dozens more galaxies. That's the Boötes void, a staggering spherical emptiness spanning 330 million light-years, where the interstellar medium is so thin it's practically a vacuum. This isn't just a quiet corner of space, it's a cosmic desert so barren that astronomers have catalogued only 60 galaxies in its expanse, compared to the thousands you'd expect in a region that size. But the real mystery isn't just its emptiness, it's what might have caused it. Some theories suggest an unfathomable collision of universes, while others point to glitches in the fabric of reality itself. The conventional explanation leans on gravitational collapse superclusters of galaxies pulling matter away from certain regions over billions of years, leaving behind these gaping voids. But Boötes doesn't fit neatly into that story. Its edges are too sharp, its interior too empty, as if something surgically removed the matter rather than letting it drift away naturally. That's where the wilder ideas take hold. One radical hypothesis proposes that voids like Boötes could be scars from collisions with other universes in the multiverse, bubble universes brushing against our own and siphoning matter away like cosmic sponges. It's a stretch, but not impossible. Quantum foam theory suggests that space-time at the smallest scales is a seething, frothy mess, with pockets of reality constantly bubbling up and dissolving. Could a fluctuation in that foam have torn open a temporary gateway, draining matter into another dimension? Then there's the statistical nightmare. According to our best models of cosmic structure, voids this large simply shouldn't exist. The odds are astronomically low, less than 1 in 10,000. That's led some cosmologists to question whether Boötes is a fluke or a sign that our understanding of the universe's large-scale structure is fundamentally flawed. Recent simulations incorporating dark energies accelerating push show voids growing faster and larger than expected, but none match Boötes' jaw-dropping scale. What's lurking in the void's depths adds another layer of intrigue. The handful of galaxies found there aren't just randomly scattered, they're weirdly clustered along filamentary threads as if huddling together for safety. Even stranger, some show evidence of recent star formation, suggesting they're not just ancient relics but active survivors in a hostile environment. How do these islands of activity persist in a near-perfect vacuum? One possibility is that the void isn't entirely empty, just filled with ultra-diffuse gas too faint to detect, a ghostly residue of whatever cataclysm cleared the space. The implications ripple far beyond Boötes. If voids like this are natural, they could rewrite our models of galaxy formation, forcing us to account for desert galaxies evolving in isolation. If they're unnatural, they might be the first tangible clues to a multiverse or something even stranger. As telescopes probe deeper into these cosmic blank spots, one thing is certain: the universe's emptiest places might hold its most explosive secrets. Deep in the heart of the Orion Nebula, infant solar systems are vanishing before our eyes, not in the slow, graceful dance predicted by theory, but in a violent cosmic evaporation. These protoplanetary disks, called proplyds, should have thousands of years to coalesce into planets. Yet new observations reveal they're disintegrating at speeds 100 times faster than anyone expected. their gas and dust boiling away like morning mist under a blazing sun. And the prime suspects, the trapezium stars, a searing quartet of young stellar giants whose ultraviolet fury is so intense it's literally blowing these baby planetary systems apart. The James Webb Space Telescope's recent thermal maps paint an even stranger picture. Rather than uniformly heating the disks, the UV radiation seems to carve them into bizarre, asymmetrical shapes, some with comet-like tails stretching light years downstream, others warped into hourglass silhouettes. It's as if the proplyds aren't just passively evaporating, but reacting to unseen currents in the interstellar medium itself. One particularly striking image shows a disk with a jagged, frost-like edge, where temperatures plunge abruptly from thousands of degrees to near absolute zero within a mere astronomical unit. This isn't just radiation at work. It hints at chaotic magnetic fields or shockwaves rippling through the nebula's gas, creating microclimates more volatile than any weather pattern on Earth. But the mystery runs deeper. Some disks are disappearing faster than the trapezium star's radiation can explain. Their evaporation rates suggest additional forces, perhaps charged particles accelerated by hidden stellar winds or even turbulence from past supernova echoing through the region. The wildest theory, these proplyds might be caught in crossfire between multiple radiation sources, their material ionized not just from above but from all sides by unseen cosmic players. The implications are staggering. If protoplanetary disks can perish this quickly, our models of planet formation may need a radical overhaul. Solar systems like ours might not be the rule, but lucky survivors of a celestial gauntlet where most perish before planets ever form. And with JWST now scrutinizing these evaporating nurseries in unprecedented detail, one thing is certain. The birth of worlds is far more tumultuous and far less guaranteed than we ever imagined. Stretching across the night sky like a cosmic serpent, the Magellanic Stream arcs over 600,000 light-years, a river of gas so vast it could wrap around the Milky Way 5 times. For decades, astronomers assumed this shimmering ribbon was nothing more than debris torn from the Magellanic Clouds, the petite dwarf galaxies orbiting our own. But recent supercomputer simulations have thrown that theory into chaos because the stream holds 20% more gas than the clouds could possibly have lost. It's as if a teaspoon spilled an entire ocean. So where did this celestial river really come from, and what does its fate tell us about the Milky Way's future? The mystery starts with the stream's sheer scale. If you combined every star in the Magellanic Clouds, they'd weigh less than 1/10 of the gas swirling through this structure. That imbalance has led to a radical new idea. The stream might not be native to the clouds at all. Instead, it could be a tendril of the cosmic web, a primordial filament of hydrogen left over from the universe's infancy, captured by the Milky Way's gravity and draped over the clouds like a stolen necklace. Think of it as interstellar driftwood snagged by our galaxy as it sailed through the intergalactic void. Evidence for this twist comes from the stream's chemistry. Unlike the Magellanic Clouds, which are rich in heavy elements forged by stars, parts of the stream are eerily pristine, almost pure hydrogen and helium, the raw materials of the early cosmos. That suggests some of this gas never passed through a galaxy before, preserving its ancient composition like a fossil frozen in time. Yet other sections do show signs of stellar pollution, creating a bizarre patchwork that hints at multiple origins. But here's where it gets even wilder. The stream isn't just drifting, it's on a collision course with the Milky Way. Within the next few 100 million years, this colossal gas ribbon will rain down onto our galaxy's disk, fueling a starburst frenzy that could birth millions of new suns. Some simulations suggest this infusion might even revive parts of our galaxy's dormant star-forming regions, like watering a parched garden. Yet others warn the influx could be messy, triggering chaotic shockwaves that disrupt existing gas clouds. The ultimate irony, this intergalactic gift might seal the Magellanic Cloud's doom. As the stream drains into the Milky Way, it could steal the cloud's remaining gas, starving them of the material needed to make new stars. Over billions of years, they'll fade into cosmic ghosts while the very structure that once connected them becomes the Milky Way's next great feast. So while the Magellanic Stream might look like a silent arc in the sky, it's actually a celestial lifeline, one that connects our galaxy's past, present, and future in ways we're only beginning to understand. Galaxies aren't just islands of stars, they're ecosystems, breathing in and out on cosmic timescales. Picture this: a massive star reaches the end of its life and explodes in a supernova, blasting its guts across space at thousands of miles per second. That material, a mix of heavy elements like iron, oxygen, and silicon, gets hurled so far it escapes the galaxy's grasp entirely, only to cool, slow down, and eventually fall back in like celestial rain. Astronomers call this process a galactic fountain, and it should be the universe's ultimate recycling program. But here's the catch: when astronomers measure the gas raining back down, it's suspiciously clean. Where are all the metals? This missing metals mystery has puzzled scientists for years. Supernova ejecta are full of heavy elements, the very stuff that makes up planets and life. So when this gas falls back into the galaxy, it should sprinkle those metals back into the interstellar medium like cosmic fertilizer. Yet observations show the infalling gas is far more pristine than expected, as if something's scrubbing it clean on its journey. One leading theory suggests magnetic fields might be at work, trapping metal-rich particles in vast, invisible loops that prevent them from rejoining the galactic disk. Imagine a sieve in space, filtering out the heavy elements before they can return. But 2023 supercomputer simulations threw a wrench into even that explanation. These new models reveal the recycling process isn't just slower than we thought, it's messier. Gas ejected by supernova doesn't follow a neat fountain and drain trajectory. Instead, it gets tangled in turbulent flows, colliding with other debris, cosmic rays, and even dark matter halos. Some of it might linger in a galaxy's halo for billions of years before trickling back, giving metals time to disperse or even get ejected again by subsequent supernova. It's like tossing confetti into a wind tunnel. What comes down isn't what went up. And then there's the wild card: galactic winds. Some galaxies, especially young, star-forming ones, generate supersonic outflows so powerful they can blow heavy elements clear out of the system entirely. These winds might carry metals far beyond the galaxy's reach, effectively deleting them from the recycling pool. That could explain why infalling gas seems so pure. It's not that the metals are being filtered out. They're being lost to the void. So while galactic fountains might sound like a tidy cosmic water cycle, the truth is far more chaotic. Metals go missing, gas takes detours, and the interstellar medium ends up with a chemical composition that defies simple explanations. As telescopes peer deeper into these recycling systems, one thing becomes clear: galaxies don't just breathe, they cough, sneeze, and sometimes lose their ingredients altogether. Between the stars, an invisible sea of scorching gas stretches across the galaxy, the warm ionized medium, or WIM. This elusive phase of the interstellar medium isn't just hot, it's fiercely energetic, glowing at 10,000 degrees Celsius while somehow occupying a staggering 20% of all interstellar space. Unlike the dense clouds where stars are born or the frigid voids between galaxies, the WIM is a paradox, a diffuse, ultra-hot fog that defies simple explanation. Where does all this heat come from? Why doesn't it dissipate into the cold vacuum around it? The answers might rewrite our understanding of how energy flows through the cosmos. For decades, astronomers assumed cosmic rays, high-energy particles zipping through space, were the primary suspect, ionizing hydrogen atoms and keeping the gas perpetually charged. But recent velocity maps from the Wisconsin H-alpha mapper, or WAM telescope, revealed something startling. The WIM isn't just uniformly glowing, it's moving with vast currents and whirlpools spanning thousands of light years. Some regions show gas streaming at speeds that shouldn't be possible without an invisible hand pushing it. That's led to a spine-tingling alternative: decaying dark matter. If certain theoretical particles are slowly disintegrating, they could inject energy directly into the WIM, heating it like a cosmic radiator while leaving no visible trace. The WAM data adds another twist. Certain filaments within the WIM appear to align with the Milky Way's magnetic field lines, as if invisible forces are sculpting the gas into coherent rivers. It's not just random heat, it's organized, almost purposeful motion. Some researchers now think the WIM could be a galactic-scale circuit, with energy from supernova or even the galaxy's core surging through these ionized channels like electricity through a wire. Yet the most baffling feature might be the WIM's distribution. Unlike other interstellar phases which cluster in dense clouds or bubble-like voids, this hot gas is everywhere, a near-constant backdrop to the galaxy. It's as if the universe has woven a shimmering, ultra-thin blanket between the stars, one that crackles with energy we can't yet fully measure. What's clear is this: the warm ionized medium isn't just another component of space. It's a dynamic, electrified layer of the cosmos, one that might hold clues to everything from dark matter's true nature to how galaxies regulate their own growth. And with every new observation, this invisible ocean of fire reveals just how much we still have to learn about the spaces between the stars. Lurking just 24,000 light-years from the Milky Way's core, a cosmic paradox defies every rule of star formation: the brick. This monstrous molecular cloud weighs in at a staggering 100,000 solar masses, dense enough to birth 1,000 stars, yet its interior remains eerily dark. Not a single newborn star flickers within its shadowy depths, as if the universe hit pause on stellar creation. What's strangest isn't just its stillness, it's the fact that, by all known physics, this cloud should be collapsing under its own gravity, fragmenting into stellar nurseries. Instead, it just sits there, a celestial vault locked tight against the chaos of the galaxy around it. The answer might lie in turbulence. When the Atacama Large Millimeter Array, or ALMA, trained its antennas on the brick, it detected gas churning at speeds that defy logic: supersonic currents racing through the cloud like invisible tornadoes. Normally, such violent motion would trigger star formation by smashing gas pockets together. But in the brick, something's counteracting it. One tantalizing theory points to dark matter, the universe's most elusive substance. If the brick is tangled in a knot of invisible dark matter particles, their gravitational pull could be propping up the cloud, balancing its internal chaos with an unseen scaffolding. Picture a balloon inflated to the brink of popping, then wrapped in an unbreakable net. Dark matter might be that net, keeping the brick suspended in perfect tension. But there's another, even wilder possibility. We might be witnessing the slow-motion birth of a globular cluster. These ancient, tightly packed stellar swarms orbit the Milky Way like celestial fossils, their origins still shrouded in mystery. If the brick is a globular cluster in its infancy, its prolonged quiet could mean it's gathering mass silently, waiting for some cosmic trigger to ignite a single, catastrophic burst of star formation. Recent simulations show such events could unfold over millions of years, with the entire cloud collapsing at once into a glittering ball of stars. The clues keep piling up. ALMA turbulence maps reveal the brick isn't just chaotic. It's layered, with different regions behaving like fluids of varying thickness. Some zones ripple with waves of compressed gas, while others appear eerily smooth, as if an unseen force is ironing out the wrinkles. Even the temperature readings baffle scientists. Parts of the cloud are colder than expected, while others flicker with subtle warmth, hinting at energy seeping in from somewhere beyond our current detection. What's clear is this: the brick isn't just an oddity. It's a challenge to our fundamental understanding of how stars, and even galaxies, are born. Whether anchored by dark matter or biding its time as a future globular cluster, this silent giant forces us to confront a humbling truth. deep in the heart of our galaxy, the universe is still writing rules we haven't even dreamed of yet. Deep in the interstellar void, far from the warmth of any star, astronomers have stumbled upon something that defies intuition: floating snow lines, vast regions where volatile compounds like water and carbon monoxide freeze solid onto dust grains, creating icy halos in the darkest reaches of space. These cosmic freezers shouldn't exist. Without a nearby star to chill the environment, temperatures in the interstellar medium typically hover just above absolute zero, too mild for most molecules to solidify. Yet here they are, glittering like frost in a sunless desert, their presence whispering secrets about the hidden forces shaping the chemistry of the cosmos. The key to this paradox might lie in magnetism. Picture a dust grain drifting through space, its surface speckled with molecules. Normally, these particles would bounce away, too energetic to stick. But if that grain is threaded by powerful magnetic fields, something extraordinary happens. Charged particles spiral along the field lines, generating tiny currents that siphon away heat, like a cosmic refrigerator humming silently in the void. This process, called magnetic cooling, could drop temperatures just enough to freeze volatiles onto the grain's surface, creating pockets of ice where none should form. It's as if the universe has invisible cold spots scattered like hidden ice caves across the galaxy. But the implications go beyond curiosity. These floating snow lines might be cradles for probiotic chemistry, the building blocks of life. In the frozen shells of these grains, chemical reactions that would fizzle out in warmer space could unfold with eerie precision. Water ice could shield fragile organic molecules from destructive radiation, while carbon monoxide snow might act as a sticky trap for atoms to assemble into complex structures. Some researchers even speculate that these regions could be where the first sugars and amino acids, the raw ingredients of life, coalesced long before planets formed. The mystery deepens when you consider the snow lines' locations. They've been spotted near turbulent gas clouds where magnetic fields twist into knots, and even in the apparent calm between spiral arms. This suggests the phenomenon isn't rare but pervasive, a hidden layer of chemistry woven into the galaxy's fabric. Recent radio telescope data reveals something even stranger. Some snow lines flicker, their boundaries shifting over time as if responding to unseen currents in the interstellar medium. Are magnetic storms rewriting these icy borders, or could dark matter interactions be subtly tweaking local temperatures? What's certain is this: the universe doesn't need stars to make ice. It has other, quieter ways to chill the void, and in doing so, it might have set the stage for life's ingredients to emerge in the most unexpected places. As telescopes probe deeper into these floating snow lines, one question lingers: how many more cosmic refrigerators are out there, silently freezing the seeds of complexity in the dark? At the heart of the Milky Way, an eerie glow pulses in gamma rays, a faint, persistent fog scientists call the Fermi haze. Discovered by NASA Fermi telescope over a decade ago, this high-energy shroud spans thousands of light years, radiating with photons billions of times more energetic than visible light. Early theories painted it as the afterglow of ancient stellar explosions or the collective breath of countless pulsars. But today, with sharper data peeling back the haze layer by layer, we're seeing something far stranger. It's not smooth. It's lumpy, clumpy, as if something hidden is stirring within it. The latest Fermi maps reveal intricate structures, blobs, and filaments of gamma rays threaded through the haze like veins in marble. These irregularities throw earlier explanations into doubt. If the haze came from diffuse processes like cosmic ray collisions, its light should be evenly distributed. Instead, these lumps suggest point sources, thousands of them pockmarking the galactic center. One leading candidate, millisecond pulsars, the ultra-dense spinning cores of dead stars, each beaming out gamma rays like cosmic lighthouses. Stack enough of them together, and their combined glow might create the haze patchwork texture. But here's where dark matter theorists lean in. If the lumps aren't pulsars but clumps of invisible matter annihilating itself, their gamma-ray signatures could match the haze uneven glow. Certain dark matter particles, like WIMP weakly interacting massive particles, should theoretically produce gamma rays when they collide and obliterate one another. The distribution of these phantom clumps nestled in the Milky Way's gravitational well might explain why the haze clusters near the core. It's a tantalizing lead, except for one wrinkle: the Alpha Magnetic Spectrometer, or MS-02, a precision instrument aboard the International Space Station, has spent years scrutinizing cosmic antimatter for hints of dark matter. Its results inconclusive. While MS detected excess positrons that could align with dark matter decay, the signal lacks the smoking gun energy profile theorists predicted. So where does that leave us? The pulsar camp argues that recent observations of gamma-ray hotspots align with known star-forming regions where pulsars should be abundant. Meanwhile, dark matter proponents counter that some lumps appear too isolated, too perfectly placed within theoretical dark matter halos to dismiss. The debate hinges on a cosmic game of hide and seek. Pulsars are notoriously hard to spot directly in the galactic center's crowded radio cacophony, and dark matter, it's definitionally invisible. Perhaps the most intriguing clue lies in the haze asymmetry. It billows farther on one side of the galactic plane than the other, as if something, a past black hole outburst, a dwarf galaxy merger, disturbed its equilibrium. That imbalance complicates both narratives, suggesting forces beyond simple particle physics or stellar demographics are at play. For now, the Fermi haze remains a riddle wrapped in gamma rays, its lumps whispering competing secrets. Every new observation tilts the scales not toward one answer, but toward a deeper realization. The galactic center isn't just a place, it's a puzzle, and solving it might require rewriting not just astrophysics, but the very rules of the universe. Racing through the Milky Way like cosmic rivers in reverse, high-velocity clouds defy the galaxy's rotation at blistering speeds of 100 kilometers per second, fast enough to cross the United States in under a minute. These rogue streams of hydrogen gas shouldn't exist. If the galaxy were a spinning carousel, these clouds would be sprinting backward against the ride's motion, their trajectories screaming defiance of gravity's expectations. The most enigmatic of them all, Complex H, a monstrous structure twice the width of the full moon in our sky, barreling toward us at breakneck speed while spinning the wrong way. It's as if the universe tossed a celestial grenade into the Milky Way's orderly dance, and we're still piecing together the shrapnel. For decades, astronomers assumed these wayward clouds were intergalactic hitchhikers, pristine gas from the voids between galaxies, finally succumbing to the Milky Way's pull. But the HI-4PI survey, the most detailed map of neutral hydrogen ever made, shattered that assumption. 40% of these clouds carry an impossible cargo, heavy elements like iron, oxygen, and silicon, the telltale ash of dead stars. That changes everything. Intergalactic gas shouldn't be laced with metals. They're forged in stellar furnaces and scattered by supernova. The presence of these elements suggests a darker origin story. Tidal debris from cannibalized dwarf galaxies, shredded by the Milky Way's gravity and strewn across the halo like cosmic roadkill. Complex H adds another layer of intrigue. Not only is it metal-rich, but its counter-rotation hints at a violent past. Some simulations suggest it might be the corpse of a dwarf galaxy that grazed the Milky Way at a steep angle, its gas stripped away and set spinning backward like a ball ricocheting off a wall. Others propose an even wilder scenario. This cloud could be surfing a shockwave from an ancient nearby supercluster, its momentum hijacked by forces beyond our galaxy. What's certain is this: high-velocity clouds aren't just passive spectators. They're delivery trucks dumping chemically enriched material into the Milky Way's outskirts, material that might one day fuel new stars or even planets. But with every new observation, the plot thickens. Some clouds show metallic compositions matching the Magellanic Stream, while others bear fingerprints closer to the galaxy's own disk, as if the Milky Way is somehow flinging its own gas into the halo and catching it again. The implications ripple far beyond astronomy textbooks. If these clouds are galactic recycling in action, they could rewrite our understanding of how galaxies grow and evolve. And if they're invaders from intergalactic space, they might be bringing clues about the cosmic web's hidden structure. Either way, one thing's clear: the sky isn't just stars and darkness. It's a battlefield of momentum and chemistry, where gas flows tell stories we're only beginning to decipher. Hidden in plain sight across the Milky Way, vast reservoirs of molecular hydrogen drift silently between the stars, invisible to our telescopes, yet outweighing all visible interstellar gas combined. This is co-dark gas, the universe's most elusive building block, and it's rewriting the rules of cosmic cartography. Traditional astronomy relies on carbon monoxide, or CO, as a tracer for molecular hydrogen. Since hydrogen itself is notoriously shy, its molecules don't emit detectable light under typical interstellar conditions. But here's the shocker: up to 50% of all molecular hydrogen exists in regions so cold and diffuse, even CO can't form. That means half the galaxy's star-forming fuel has been hiding in the shadows, undetectable by conventional surveys. So how do you map the invisible? Gamma rays hold the key. When high-energy cosmic rays particles accelerated to near light speed by supernova and black holes collide with hidden hydrogen, they produce gamma rays like cosmic flashbulbs illuminating unseen structures. NASA's Fermi telescope has spent years capturing these faint signals, revealing sprawling rivers of co-dark gas threading through the galaxy's spiral arms. Some filaments stretch thousands of light-years, weaving between known clouds like phantom highways. And the real surprise: much of this gas lurks in the so-called CO dark zones, regions where astronomers once assumed the interstellar medium was too sparse for molecules to survive. The implications are staggering. If co-dark gas is this abundant, our models of star formation might be missing half the ingredients. Cold, diffuse hydrogen could act as a stealth reservoir, quietly funneling material into denser regions where stars ignite. But the mystery deepens when you ask why standard tracers fail. The answer lies in chemistry's fine print. For carbon monoxide to form, carbon and oxygen atoms need enough energy and density to collide and bond, conditions that simply don't exist in the galaxy's quieter neighborhoods. Hydrogen, meanwhile, pairs up effortlessly even in the thinnest gas, creating H2 molecules that slip through our observational nets. Innovative techniques are finally bringing this shadowy realm into focus. By combining gamma-ray data with infrared surveys which catch the faint heat from dust grains mixed with the gas, scientists are assembling the first true maps of the Milky Way's hidden skeleton. Some teams are even using cosmic ray proton collisions as a measuring stick, since the rate of gamma-ray production depends directly on the amount of hydrogen present. These methods reveal co-dark gas isn't just filler. It's dynamic, clumping into structures that could seed future stellar nurseries or even shield fragile molecules from destructive radiation. Yet every breakthrough raises new questions. Why does some co-dark gas cluster in unexpected voids far from known star-forming regions? Could magnetic fields be corralling it into invisible holding pens? And most provocatively, does this missing mass hint at even darker components, like hypothetical dark hydrogen, in forms our instruments can't yet grasp? For now, the galaxy's hidden hydrogen remains a silent partner in cosmic evolution. Its whispers only just reaching our telescopes, but as detection methods sharpen, we're peeling back the veil on the universe's most overlooked ingredient, one gamma-ray flash at a time. Rising from the galactic disk like colossal smokestacks, chimneys of superheated plasma stretch over 1,000 light-years into the Milky Way's halo cosmic megastructures, acting as escape valves for the galaxy's pent-up energy. These towering tunnels, first mapped in stunning detail by the E-Rosetta X-ray telescope in 2023, aren't just passive conduits. They're part of an intricate ventilation system, ferrying hot gas, magnetic fields, and even cosmic rays from the star-birthing frenzy of the disk into the calmer outskirts above. What's truly groundbreaking isn't just their scale, it's how they're intertwined with radio-emitting filaments, a pairing that suggests the Milky Way doesn't just leak energy haphazardly. It exhales in precise, rhythmic bursts as if breathing on a galactic scale. The discovery began with a eureka, a moment in the E-Rosetta data. X-ray maps revealed paired columns of million-degree gas erupting from the galactic plane near the constellation Norma, each chimney perfectly aligned with known radio loops, giant, magnetized structures first spotted decades ago but never fully understood. This correlation cracked open a new paradigm. The radio loops might be the magnetic skin of these chimneys, shaped by the same outflowing energy that heats the gas. Picture a steam pipe wrapped in electrified wires where the steam is plasma and the wires are cosmic magnetic fields crackling with unseen currents. Together, they form a feedback loop, regulating how the galaxy distributes the heat and turbulence generated by generations of supernova. Supercomputer simulations bring this process to life. When researchers modeled the Milky Way as a dynamic ecosystem, where stars live, die, and explode in cycles, they found these chimneys aren't static, they pulse. Gas surges upward in waves, triggered by clusters of supernova detonating in sync, their combined force punching through the disk's denser layers like geysers erupting through bedrock. Between these eruptions, the chimneys even appear to inhale slightly, drawing in cooler material from the halo that later gets reheated and expelled again. It's a celestial respiratory system, with each breath lasting millions of years. The implications ripple far beyond astrophysics. These structures might solve the long-standing mystery of galactic missing energy, or why the heat and cosmic rays produced by supernova don't simply overpressurize the disk and halt star formation. The chimneys act as release valves, preventing the galaxy from choking on its own exhaust. Even more tantalizing, their existence hints that feedback loops like this could be universal, woven into the fabric of how galaxies grow and self-regulate. The Milky Way isn't just a collection of stars, it's a living engine, with these chimneys as its exhaust pipes, quietly governing its evolution. Yet for all we've learned, the chimneys still guard secrets. Why do some regions show multiple stacked vents like floors in a cosmic high-rise? Could dark matter's gravity be shaping their paths? And most provocatively, if we could see our galaxy edge on, would these structures form a perfect symmetry, a mirror of energy flowing above and below the disk? For now, the chimneys stand as silent sentinels, reminders that even our home galaxy still has stories left to tell. Running through our galactic neighborhood like a cosmic scar, the so-called dog-leg anomaly bends the Milky Way's magnetic field at a jarring angle, a 150 light-year kink in what should be smooth, flowing lines of force. This isn't just a wrinkle in space, it's a full-blown structural defiance, as if the universe took a ruler to the local arm's invisible scaffolding and snapped it in half. What could warp the galaxy's magnetic backbone so violently? The answer might lie in two radically different possibilities, one born from stellar destruction, the other from the universe's most elusive substance. First, the explosive contender, a relic supernova shockwave. Imagine a dying star detonating with such ferocity that its blast carved a permanent dent into the interstellar medium's magnetic fabric. Over millennia, the expanding shell of debris could have plowed through surrounding gas like a snowplow, dragging magnetic field lines into its twisted wake. Supporting this, Planck satellite data reveals a striking alignment of dust grains along the dogleg's edges, a telltale sign of past turbulence. When supernova shockwaves pass through interstellar dust, they act like cosmic combs, arranging particles into orderly rows that polarize starlight in predictable patterns. Planck's polarization maps show exactly this signature along the anomaly, suggesting something violent once ripped through here, but there's a twist. Some regions of the dogleg exhibit polarization angles that don't quite fit a clean supernova model. The field lines aren't just bent, they're braided, as if an unseen hand knitted them into knots. That's where the dark matter hypothesis links in. Simulations suggest dense clumps of dark matter, invisible, gravity-rich substructures peppering the galaxy, could warp magnetic fields by sheer gravitational shear. If one such clump drifted through the local arm, its pull might have twisted the field into this bizarre configuration, like a ship's wake distorting ocean currents. Intriguingly, the dogleg aligns with a statistical overdensity in gravitational lensing surveys, a subtle hint that something massive but unseen lingers nearby. The most tantalizing clue, temperature. Planck's dust maps show the dogleg's coldest patches coincide with its sharpest magnetic kinks. Supernova remnants typically leave behind heated gas, not frigid dust. Unless, of course, something is cooling the region actively. Could dark matter interactions be sapping thermal energy from the area, leaving these icy fingerprints? It's a long shot, but if proven, it would mark the first indirect detection of dark matter's microscopic physics sculpting macroscopic structures. For now, the dogleg remains a cosmic Rorschach test. To some, it's a fossilized explosion, a stellar death etched into the galaxy's magnetic skin. To others, it's a shadow puppet cast by dark matter's invisible hands. Either way, its very existence proves that even the quietest corners of the Milky Way hum with hidden violence, and that the interstellar medium's calm facade masks a reality far more dynamic than we ever imagined. Stretching across Orion and Eridanus like a monstrous bite taken out of the Milky Way, the Orion-Eridanus supershell gapes over 1,000 light-years wide, a cavity so vast our entire solar system could orbit inside it without grazing the walls. This isn't just empty space, it's the aftermath of cosmic devastation, a region where something, or many somethings, scooped out the interstellar medium with unfathomable violence. The math is staggering. To carve a void this size would require the energy of roughly 100 supernova exploding in concert. Yet when astronomers scan the area for the expected graveyard of dead stars, they find only a handful of remnants. Where are all the corpses from this celestial massacre? The answer might lie in the supershell's very shape, not a perfect sphere, but a jagged, irregular bubble with tendrils stretching into neighboring gas clouds. This suggests the original explosions didn't happen all at once, but in waves over millions of years, their shockwaves piling up like a snowplow building a drift. Each supernova's blast front would have compressed surrounding gas, triggering the collapse of dense pockets into new stars, some of which then exploded in turn, perpetuating the cycle. It's cosmic cannibalism, stellar deaths breeding stellar births in a self-sustaining chain reaction. The missing remnants, perhaps blown clean out of the region by later explosions, or dissolved into the turbulent froth of the interstellar medium. But the Orion-Eridanus shell isn't just a fossil. It's still evolving. ALMA radio telescope images reveal its outer edges are festooned with delicate filaments, threads of gas, and dust where the shock front is currently bulldozing through nearby molecular clouds. In some spots, this compression has birthed entire stellar nurseries, their infant stars flickering to life in the wake of the expanding wall of destruction. Imagine a wildfire tearing through a forest, but where the flames pass, new saplings immediately sprout from the ashes. This is galactic ecology in action, where destruction and creation exist in perfect, brutal balance. The most mind-bending revelation comes from Gaia spacecraft data. By tracing the motions of stars near the supershell, astronomers discovered something unexpected. Many are moving in synchronized streams, as if entire stellar families were flung outward by the same ancient cataclysm. These runaway stars might be the smoking gun pieces of the original star clusters that hosted those 100 supernova, now scattered like shrapnel across the sky. Their trajectories point back to multiple epicenters within the shell, hinting at not one coordinated burst of destruction, but a rolling storm of stellar deaths rippling through the galactic plane. What emerges isn't just a story of chaos, but one of astonishing regulation. Supershells like Orion Eridanus may be the galaxy's pressure valves, cycling energy and heavy elements from generations of stars back into the interstellar medium. They're not merely holes, they're engines, reshaping the galaxy's structure and chemistry with every expansion. And as the next generation of telescopes probes deeper, we're left with a humbling realization. Even the emptiest corners of space thrum with the echoes of violence that gave them form. The Vela pulsar should be one of the most reliable beacons in the cosmos, a spinning neutron star flashing Earth 30 times every second with metronome-like precision. But in August 2021, something bizarre happened. Without warning, its X-ray emissions vanished for a full 16 seconds, not dimmed, not flickered, but switched off completely, before roaring back to life as if nothing had occurred. This wasn't some instrument glitch. Multiple telescopes confirmed the blackout, capturing the exact moment when one of the universe's most predictable clocks simply stopped ticking. What could possibly silence a pulsar, an object so dense its magnetic field could strip data from every credit card on Earth at half the moon's distance? The prime suspect is an invisible cosmic prankster, plasma lensing. Picture a vast rogue cloud of superheated gas drifting between Vela and Earth, its turbulent layers acting like a funhouse mirror for X-rays. As the cloud's density fluctuates, it could refract the pulsar's high-energy light away from our line of sight, creating temporary eclipse-like blackouts. The phenomenon wouldn't affect radio waves, explaining why other telescopes still detected Vela's regular pulses during the X-ray dropout. It's akin to someone turning off a spotlight while leaving the stereo playing, a disconnect that points squarely to something warping the signal en route. Yet there's a wilder possibility lurking in the data. The abruptness of the cutoff, less than 12 milliseconds, hints at processes within the pulsar itself. Some theorists argue this could be evidence of a magnetospheric quake, where the neutron star's crust, under unimaginable strain from its own rotation, momentarily fractures. These quakes might temporarily reconfigure the pulsar's magnetic field lines, redirecting particle jets that normally blast X-rays toward Earth out into space like a fire hose suddenly kinked. Supporting this, archival data reveals similar, though shorter, dropouts from Vela in 1988 and 2008, suggesting a cyclical pattern, perhaps tied to decades-long stress buildup in its rigid crystalline crust. But the plot thickens when you examine other pulsar anomalies. In 2023, the nearby J0835 pulsar exhibited the opposite behavior. Its X-ray emissions surged by 600% for exactly 43 seconds, as if someone had cranked up its internal dynamo. These paired mysteries, sudden silences, and unprovoked flares suggest neutron stars might harbor dynamic, hidden layers of plasma or superconductive fluids that occasionally short-circuit their emission beams. Imagine a lighthouse where the bulb doesn't burn out, but the mirrors controlling its beams sporadically warp or wobble, casting the light off course. The stakes go beyond stellar curiosities. If plasma lensing is to blame, these events could map otherwise invisible structures in the interstellar medium, dense plasma clouds that don't emit light but reveal themselves by bending it. Conversely, if magnetospheric quakes are the culprit, we're glimpsing fundamental physics at the edge of possibility, matter so compressed it breaks the rules of conventional materials. Every flicker, every dropout from these cosmic lighthouses isn't just a glitch, it's a telegram from the universe's most extreme environments, written in a code we're only beginning to crack. So while the Vela incident may have lasted mere seconds, its echoes ripple through astronomy. It reminds us that even the steadiest celestial clocks can harbor secrets, and that the interstellar medium isn't just empty space, but a labyrinth of hidden forces waiting to rewrite the rules when we least expect it. For centuries, stargazers mapped the heavens in two dimensions, dots on a flat celestial sphere. But today, a revolution is unfolding as Gaia, JWST, and atomic line surveys stitch together the first true 3D atlas of the interstellar medium, peeling back the galaxy's layers like an infinite cosmic onion. Gaia's billion-star census doesn't just track positions. It measures starlight reddening caused by dust grains, allowing astronomers to reconstruct the Milky Way's veils of obscuration in 3 dimensions. Pair this with JWST infrared eyes piercing through those same dust clouds, and suddenly the interstellar medium transforms from a vague haze into a labyrinth of nested filaments, bubbles, and voids. Yet the most startling revelation comes from atomic line surveys like GBT's Hi4Pi and ALMA molecular maps. By cataloging the faint radio whispers of hydrogen and carbon monoxide, these projects reveal gas clouds drifting between the stars, some so diffuse they'd vanish if not for their spectral fingerprints. The magic happens when cross-referencing these gas maps with Gaia's dust data. In theory, every dust particle should have a gas counterpart, but here's the anomaly. 30% of the galaxy's dust extinction has no detectable gas association. It's as if the universe scattered invisible soot across interstellar space, challenging our basic understanding of how dust forms and survives. One radical explanation. Dark gas molecular hydrogen, so cold and spread out it evades traditional CO surveys, yet still clings to microscopic silicate or graphite grains. Another theory points to supernova shock dust, where stellar explosions forge hardy particles that persist long after their parent gas clouds dissipate. The wildest hypothesis involves interstellar, fluff, porous, fractal dust structures built like cosmic snowflakes, with so much empty space between their branches that they obscure light while barely registering in gas emission surveys. This missing matter mystery underscores why next-generation projects like the Square Kilometre Array or SCAR could rewrite the rules. With sensitivity to detect hydrogen 20 times fainter than current limits, SKA might finally spot the phantom gas haunting our maps. Its phased array antennas will also trace magnetic fields threading the interstellar medium, revealing how invisible forces sculpt dust into the unexplained patterns we see today. Meanwhile, upcoming X-ray polarimeters like IceCube could track dust grain alignment, clues to whether galactic magnetic fields are braiding these rogue particles into hidden architectures. The deeper we probe, the clearer it becomes. The interstellar medium isn't just a backdrop. It's a dynamic, multidimensional ecosystem where dust and gas obey different rhythms, and where every new 3D map unveils more questions than answers. As these projects converge, we're not just charting space, we're decoding the invisible forces that shape it. We've journeyed through the interstellar medium's greatest enigmas, from colossal gamma-ray bubbles boiling out of the Milky Way's core to ghostly snow lines freezing in starless voids. We've watched pulsars vanish mid-pulse, traced magnetic kinks that defy physics, and stumbled upon invisible rivers of gas with no known source. Yet here's the humbling truth: every answer uncovers deeper questions. The interstellar medium isn't just empty space, it's a dynamic, chaotic frontier where dark matter might sculpt gas clouds, where dying stars rewrite magnetic laws, and where entire chunks of chemistry hide in plain sight. Think about this: nearly half the normal matter in our galaxy floats between stars, ghostly and diffuse, resisting detection. The universe's most basic ingredients, hydrogen, carbon, even the building blocks of life, drift in forms we're only beginning to map. And the forces at play, they're stranger than fiction. Magnetic fields stronger than logic allows, plasma chimneys exhaling galactic energy, and dark molecular clouds so dense they should collapse yet stand frozen, as if time itself paused. What's out there right now, in the blackness between the stars, signals we can't decode. structures we've never imagined, phenomena that don't fit any equation in our textbooks. That's the thrill of cosmic exploration. The universe always keeps a few cards hidden. So tell us which mystery pulled you into the cosmic unknown, the Fermi bubble's gamma-ray glow, the bricks' starless defiance, or something else entirely. Drop your thoughts below, and if you're ready for more deep space revelations, hit subscribe. The universe isn't done surprising us, and neither are we.